Okay. Okay, it looks like it's working now. I'm sorry about the delays. Always takes a little bit longer to get started than one wishes. And here I wanted to. Let me download the module. Shows up there. Show up here. There. So last, last time we had talked about group project. I have put a link here. I created a term paper topic selection. So you can select your topics. So I've listed the topics here. So the easiest way is to probably just click there. And put email address if necessary. And the last 4 digits of your student number, your family name, your given name. And here it should automatically have the value of the topic you selected. So if I went to topic 9, application of fracture mechanics, it should have the topic 9. So this part, you should not have to select it. Okay, so you just need to go on here and go through the list of topics and select other topic. And after a few minutes, it may take up to 5 minutes, you should see your name appear on the topic you have selected. Okay, so that's how you can the most easily, I think, make the selection of topics. So it's already live, and eventually you will be able to find there the, who else has selected that same topic. Okay. So that part should already be, yes.
Can I just change the topic when after I select?
Yes, and when you change the topic, to change the topic, I think you, if I recall, you just need to select another topic and put your name, and it will use the last whenever it is an instance of your student number, it's the last 4 digits of your student number. So whenever it finds the last instance of your student number, that's the topic it will be assigned to your name. Okay. It's just a Google Sheets thing. So that's the kind of thing you can do just on a spreadsheet, by the way, without any background programming. It's just spreadsheet formulas. So appreciate how powerful they can be even as plain plain instruments like this. So that should cover that part. Okay, so let me see what we had here. That I need. Uh, in case I need to draw things on the blackboard. We will use this virtual blackboard here to draw things. That way it will be recorded for everyone. It's not the most convenient, but it works. And if we need to work on spreadsheets, I don't think we'll have today, but we'll have this other one. So open board and perfect. So for now, so these first classes are just basically to present a bit of terminology, and so that when you do your readings, you can follow if you're not familiar with the terminology that may be used. So we are going to be concentrating on those. So we're gonna cover a little bit of continuum mechanics, elasticity, plasticity, creep. The laws of continuum mechanics. Let me make sure I have the. Wanted to make sure I had the correct set of slides. So the laws of continuum mechanics cover the conservation of mass, conservation of momentum, and conservation of energy. And that is what is used to solve a number of problems in different fields, whether you're talking about mechanical resistance, you're talking about diffusion or heat transfer. You're talking about diffusion of toxic elements, etc. So you will always use the same basic principles to solve all these problems. What you use in continuum mechanics is usually tensor notation. And what can you represent with tensors? Well, you can represent the full state of stress at a point, or the state of strain, at a point, the temperature at a point. I mean, temperature is easier in a sense because it's a scalar value in itself, but even the scalar can be represented as a tensor. A force acting at a point on a structure, velocity acting on a point in a body. So what are tensors? They are classified by rank or order, and the basic tensor is the numbers that you know, which are known as scalars. So that's a tensor of order 0. It's just a number. Okay? It's still a tensor. Okay. When you have order one, you talk about vectors. So vectors will have a sequence of values. And when we talk about vectors in space, usually they have three components, but the vector can have multiple components. It can be much fancier than that. So, but it still has only one dimension itself. So the representation of the notation, even if it's a vector in 3D space, the vector itself is a one-dimensional tensor because it's a simple sequence of numbers. Okay, the numbers may represent the scalar in each of the axes of space, but together they are in a single sequence of values, so that's a vector. Second order tensor is identified as a matrix. We have rows and columns making a table. That's the most common tensor that we use. But technically, we could go into third order tensors, which would be in a cube, for instance, the voxels in a cube. So if you had numbers not only making tables, but we have tables stacked onto each other, we now have a third dimension tensor. By the way, in the spreadsheet LibreOffice or OpenOffice, you can actually use them as third order tensors because the sheets themselves can be referenced in order. So you could refer to a range not only as a row, a column, but also across sheets. You can define the same cell across sheets or the same range of cells across sheets can also be used that way. So technically, with LibreOffice or OpenOffice, you can make a third order tensor. So each sheet is thought of as a sequence in the third dimension, basically, of the tensor. Obviously, for most practical purposes, a matrix is good enough as the highest order we will typically use, but the tensor notation will represent as a tensor any of those values. So there are different types of operations we can apply on some tensors. In particular, we have defined, and this should be a review for all of you, but of course it can be years since you've last seen it. So we'll go over a brief definition of the basic vector operations. Okay? So you can obviously add vectors. And how do you remember how it works when you add vectors? Say that I have a vector 3, 4, 7. And I have another vector which is 5, 8, 9. So that's the two vectors in space. If I add them together, what will I get? Yeah, oh, yes, the result will be a vector. Good. But specifically, what will it look like? How do I mechanically add two vectors together?
Add I component of 12, like 8 to 12.
So this is the component I vector ijk, say?
8 to 12, 16.
Okay, so if I add them, it will be that plus that.
8 to 12, 16.
Okay, so that's a big plus there. 8, 12, 16, that's the result. Okay. So let's say that I want to subtract those vectors. How do I do it? In the same way, right? 3 minus 5, and I repeat for each of the component. Okay, that's fine. Now, we go a little bit more challenging. So let's say we want to multiply Sorry. I want to multiply these vectors. What's important to specify before I can multiply the two vectors? Is there something special about vector multiplication?
Two types of multiplication.
There's two types of multiplication, right? So there is the dot product. So let's just put the asterisk for now for dot. Actually, can I use this? Yeah. Okay, so if I use the dot product, how does the dot product work?
Right. Two vector to get a number, or multiply two vector to get a number.
So it's the sum of the multiplication of the two, yes, and we get a single scalar value. So that's important to know that the dot product is a scalar value. What's also important to know is that if we have the two vectors expressed in terms of an angle theta, right, in space, then we use the magnitude of A and B, we can multiply the size of the two vectors together, and we multiply that by the angle of the two vectors, and it will give us the result. So A and B are no longer a vector. Notice one thing, that I have A and B as bold characters. It's really important, okay? You will always represent, or you will see in text, tensors represented with bold variable names. And if it's not bold, it's not a tensor, it's a scalar. Okay? It's a very important distinction to note. So if it's a vector specifically, sometimes you will have a little arrow instead on above it. But if it's bold, it will be a tensor of some sort that is not a scalar, okay, of order greater than 0. Okay. So it's a single value and it's a scalar. When you have the cross product is a bit more complicated, and it is a vector. The vector has the particularity to be perpendicular to the angle. So if I have the first vector, I use the right hand, it's the right hand rule. So two ways of thinking about it, the first vector, the second vector, and then the output goes in the direction of your third finger perpendicular to your hand. Also, still with the right hand, if you align with the first vector, you curl it towards the second vector, and then the thumb is pointing in the direction of the resulting vector. It's an important little detail. I also like to use it when I'm doing surveying. Say that I have coordinates in easting and northing. And if you're familiar with road work, how do you report for any road work? How do you report coordinates for the job site?
East and north, of course.
Easting and northing. That's a general surveying approach, but for a specific job related to roads, what is the kind of coordinates that we use?
They have station 0 and then they will move.
They have stations and offset, okay? When you're talking about roads, on a given project, on a given segment of project that you are dealing with, you will have the easting and northing of control points. But the project coordinates, okay? Once the control points are there just to tell you to reference your job to the overall world, right? But the job itself will be in terms of easting and northing. So let's say I have the station and offsets. So let's say that I have these control points. It's on the median. Typically, you will have some control points along the center line of your roads, along the median. So I have here easting of the first point and the northing of the first point. And here I have another for the end of the segment. I have another value for easting and northing. So now I have a number of control points that I have from my map. So as a designer, I have them in terms of easting and northing, but I want to present them to the work crew in terms of station and offset so that it's easier because on the field, they will have stakes at every full station, right? So if this is 3 plus 479.56, then they will make sure to have a stake at 3 plus 480, exactly, right? And then they will have another one at 3 plus, if they're going by 20 meters, 500, or if they go by 10 meters, 590, let's say it's every 20 meters. So those will be stakes that will be marked on the project. And so you can measure the station between those stakes, and then you can measure an offset. An offset is perpendicular. So you have those stakes. And perpendicular to that, either right. So if this is increasing in station, then we always look towards the first station is lower. We always point from lower station towards higher station. And now this becomes offset to the right and offset to the left. And so we measure this offset. So let's say that I have a few boreholes that I want made, or I have some structure to be placed. And on my plan, I know the easting, call this P1, northing P1, easting P2, northing P2, and I may have a number of those, right? And I want to convert these eastings and northing into stations and offset. So you can do it without any sort of trigonometry. Okay? Because the first thing you may think of is to take this, calculate the angle, figure the cosine. So if you figure the cosine, you will get, I have the length of one, but I just want this one. I don't want the length of that one because I don't want the product of two vectors. I just want the cosine of this line, right? So I don't want A times B, I want 1 times B. So what I do is first, I find the vector, let's call this AB. So the vector AB will basically be in this in the plane, it will be E1 minus E naught and 1 minus N naught. And we assume that this is on the plan because this is done on the flat plan, on the 2D plan, so elevation 0. So I now have my vector. Of course, it's in 2D, so I don't really need the 0, but it becomes essential when I want to use a cross product to have that third dimension. Right? So I can now have this value. So if I calculate the length of the vector, okay, which is E1 minus E naught square plus
And 1 minus and the other.
so I calculate this once, okay? This is the length of AB. I divide this over the length of AB,
Get unit vector.
AB, and I have the unit vector. So now I have a unit vector that points in the same direction as AB. Okay, and now I can use the unit vector of AB times the vector EP at P1, which is at EP minus E0 and P1 minus N0 and 0. So I have now a second vector. So this one I calculate once, the unit vector. Even if I have 200 points here in between these 2 points on the station, I calculate only the unit vector once, and then I can just do the vector multiplication, the dot product. And the dot product is super easy, as you said. It's oops, 7. The dot product is this times that plus this and that plus I will show you 2 ways of doing it on a spreadsheet. You do exactly the same thing. Plus. Okay, I see. Okay, it's 110. It's a scalar. Right? I could have said also some product of this and this. And it does exactly the same thing. Okay, so some product of 2 vectors does the product of each element and adds them together. So some product is basically the dot product when you have two vectors. It's a nice function that does mechanically the product plus the product plus the product of each terms in 2 vectors that are, it can be in rows, can be in columns. Okay. So it's a function that I noticed not everyone knows on a spreadsheet. So I like to introduce you to it because it lets you do a very fancy things. So you can really easily set up these kinds of conversions on a spreadsheet. And finally, we have the cross product. And if I had to do the cross product, so let's say for fun, yes. I will do it at the end, yes.
What is the physical like representation of this 110?
It's the product of, okay, the 110 is the product of, so we have vector in space 3, 4, 7. And then we have the vector 5, 8, 9. On the plane, if we find the plane that is common to both of them, they are separated by an angle, it's the projection of one on the other. Okay, and we multiply this projection on top of the so the length of that projection by the length of the other vector. It's easier. Okay, it's easy to think of it here. Okay, when I have a unit vector, its length is 1, right? And I multiply 1 by the projection of this on here, right? I multiply 1 by this, which is equal to it, right? So I just get this length. When you're not using a unit vector, that length is not 1, so the product here would be larger if it was bigger than 1 or smaller if it was smaller than 1, right? But it's using one of them as a multiplier guide, and we multiply the other by the projection and scale it, basically. It's like this is a rubber band, the guiding, the line onto which we project it onto this line, and if it's not unit vector, we're stretching. After projecting it, we're stretching it by the length of that vector. Okay, by the how much that vector is bigger than 1 is how much we stretch. Okay, so it's a projection with a stretching. That's what physically it is. Now the offset we can actually use. So the offset is this part here, right? And you will notice that in the cross product, we have the length of A times length of B times the sign between them. So that looks exactly like the other one, except that instead of being the projection of this, it's the length of that, over the length of this vector, multiplied by the length of the, so we are still stretching it by the length of this vector, right? We're still stretching it by how much this one is bigger than one, okay? But instead of taking the projection and stretching that, we take this and we stretch it by that much, okay? By however much that vector is bigger than one. So by making it a unit vector, it is always one, so it's just this length. But then we multiply it by a vector which is perpendicular to the plane on which A and B are found. So if this is a horizontal plane, and it is because that's why I put a 0 at the end to force it to be always on the horizontal plane. Okay? So by putting it on the horizontal plane, I know that it will be a vertical line. So I am cheating in a way by saying it's the offset. It's not pointing in this direction, right? It's pointing either out or into the board. But because mathematically the rest of the equation is basically the sign, as long as I use a unit vector, right? I'm using this offset. What I will do is, as long as I use the right hand, a positive value will be offset to the right. I interpret it as offset to the right. And if it was negative, I would say offset to the left. As long as I start with this vector, so this one has to be first, so that one has to be A. And the second vector is the unit vector. In that case, positive is right, and just because of this. So this is one example of, I mean, in numerical methods, there's many ways you can use these, but this is one of the most practical ways that I found to calculate easily stations and offset of coordinates when I want to put them on a map. Okay, so this is an everyday kind of conversion that an engineer might have to do if you're doing any kind of road construction related work. This kind of construction, I had to do it for work. This is where I came up. I didn't feel like calculating angles every time, and you go calculate cosine, go back, blah, blah, blah. Why I need to calculate the sine and cosine or calculate an angle, first of all. I just doing these mathematical operations. You skip completely the trigonometry. Okay, so it makes the calculations much simpler. And what is fun, so we'll check here. What is the cross product? Okay, so cross product would be I. So I minus J plus K, right? So I times, so what is the cross product? 3 times 8 minus 4 times 5, correct? Plus J, minus J times 3 times 9 minus 7 times 5 plus K times 3 times, sorry, did I say, oh, sorry, I put the wrong one. It's 3 times 8 minus 4 times 5. The I should have been, sorry about that, 4 times 9 minus 7 times 5, right? 8. Sorry. Yeah. Okay. So that is the cross product. Obviously, when you set it up, it's easy. Okay. So if I were to do the cross product here, I would have to have the A is for the, so let's copy IJK is what I want. Okay, so IJK, oops, there you go. And so here we say, so I is 4 times this minus 7 times. Here, this is 3 times 9 minus 7 times 5, and of course, that's minus. Right, so 3 times 9 minus 7, and the last one is K is 3 times 8 minus 4 times 5. Right? Okay, so this is what it would give you. Now, what if you're on the plane? Okay, because all of these are on the plane. On the plane means that the last value is 0 and 0. What do you notice? You only have the last term that will give you a value, which is what you want. You only want one term, right? So you know that it has to be perpendicular to them. So in the plane, it will have no length. So whenever you have something like this, basically what you have is just you look at your vector that you have between this and the unit vector. So the unit vector has to be multiplied second, right? And so you just have the terms of your unit vector and the other one that you multiply together without considering the zeros. Bang, you get directly a single value. You don't care that it's K or whatever, because all you want is the offset. So in the case of a plan, it's super easy to set up your X, easting, northing, station, offset in the table, just simple formulas based on this. Okay? So I wanted to show you that as a practical application of these operations, because we see them sometimes in a very abstract way. We talked about vector multiplication and we don't always see what they mean. So this is essentially what they are. So it is a projection. In this case, when it's a unit vector, it's pointing this way. And if it's not unit vector, it's also stretched by the length of the vector. Right? And in case of the dot product, it's a scalar, so it's not pointing anywhere. Okay? The cross product is pointing this way, but the dot product is not pointing, it's a number. But the value that it has is the projection of this onto this one multiplied by the length of that one. When the length is 1, when you have a unit vector, you can do all kinds of fancy geometry with it. You can set up a quick spreadsheet, no trigonometry, calculate directly your stations and offset for a segment of road. So there is no division in terms of the vector division. However, when you express a vector as a matrix, if you find or if you have a tensor, sorry, you can always have the inverse of a tensor. In this case, when you have the inverse of a tensor, you multiply it by another tensor, and that is how you effectively do the equivalence of division with tensors. Okay, that's why matrix inversion is a very important operation. It can be complicated to do. I'm sure everyone remembers exactly how you do matrix inversion, right?
As if you are, you put like oblique and it changing.
Yeah, basically. I mean, there's other algorithms, but the basic one that you can use is, so you can only invert a matrix that is square. And so you have one. Okay, these are the coefficients. To work with it manually, what you do, you make an inverse matrix. So you want to have the unit matrix here that has one on the diagonal. And the idea is to convert this into this. And all the operations that you do on this, you apply to this. So let's say that I start by dividing everything by A1 on my first row. So I have to say A over A1, 0 over A1, which is 0, 0 over A1, which is 0. Okay? And then I say, well, now this is 1, A1 over A1 is 1. Okay? And now you say, well, I subtract B over A1. So minus B over A1, so this becomes 0. But you have to, no, sorry, you would have to do it on everyone. Anyways, the point is that you do all the operation, whatever you do on a row, you have to do on the whole row. If you divide one row by the other one, so you can say this, the minus the next one, so the next one you also make it so that it's 1. And then 1 minus 1 will be 0, so if this is 1 minus 1, so this one will be 1, so this one will be B2 over A2. And this one was B1 over A1, so B1 over A1 minus B2. Sorry, it's this one minus this one because we want this to be 0. So minus B1 over A1 minus B1 over A1 minus B1 over A. So you have minus all these terms. So this one will be this one. Yeah, this one minus this one, right? So you end up having terms, you play with all the terms so that this ultimately becomes 0, 1, 0, 0, 0, 1, and all these operations you apply on the other side. And when this is the unit matrix, this is your inverse. Now there's more fancy terms that we use, the cofactors and so on, but we're not going to go over that. You can always make an algorithm to find the inverse of a matrix using just these methods. It works. And it can work. It can work not that slow. I did it for fun once on a spreadsheet, and it turned out to be faster than the built-in inverse one. I thought it was going to be so slow, but it wasn't as bad as I thought for small matrices. Now, talking about the matrices, sometimes you will find there's some rules of notations. So any index, whenever you have a term, so you will either have the tensor represented as a bold variable, or you'll have a variable with indices, okay, depending on how many dimensions your vector has. And if an index appears only once, it's called a free index. And if it appears twice, it's called a dummy index. So if you have the same index II, that's a dummy index and it's fabricated. You will also encounter the Kronecker delta. And the Kronecker delta is a special variable that is basically one if I and j are equal and 0 otherwise. So it basically always will give you a unit matrix. Right? But it's a function basically that is as large as you need it to be to always give you a unit vector, a unit matrix, sorry. Okay, so if one index is a free variable, the other one, basically you can be inverting a matrix or another tensor in that way. IJK are the standard vectors that we use to represent the 3 dimensions of space. And you can represent a vector with so you can either represent a vector with an arrow or in bold. Some other values or operators you're going to find is the gradient operator, which is an inverted delta. And you apply the gradient to a scalar field. But the resulting is a vector. So you have pressure distribution in saturated soil. That's your scalar field, is the pressure. The gradient is the resulting vector, and the gradient will point in the direction in which the flow is going at any given point. Okay, so it looks basically at the difference in pressure in all directions, and it will have 3 different components that resolve into a single vector. Okay, so the pressure field is nothing but a field of scalar, right? You have numbers everywhere. There are scalar values. You can measure the pressure at any point. It doesn't have a direction, the pressure itself. But the resulting gradient is a vector field. And so when we apply it to a scalar field, we get d of a over dx. So the gradient is a very common operator. Okay. And it's written in a very similar way as the divergence. And the divergence can be written as the divergence of the tensor or this way. You notice the difference between the 2 notations?
This is a scalar, so it's a dot.
So the other one is applied to a scalar. This is always applied to a tensor. And because it's applied to a tensor, here we have the dot product essentially. Okay, so so we have d of dx, so it's the dot product of the operation on each. So we do like in the case of the gradient, but we drop the vector part and we add all the values like in the dot product. Like in the dot product, we sum the individual component, and what we get out of it is a scalar. Now, what do you use the scalar for? Let's say we apply the gradient to get the Darcy flux of water in the soil, right? And we want to find if there's a change in water storage in a given element. So, well, what is the change in water? Is the amount of water, or is the temperature increasing or decreasing at a given point due to the change, right? So we look, well, the vectors tells me that there's a change in pressure in water in volume of water or in temperature in this direction by so much, in that direction by so much, in that direction by so much. That's what the gradient is, right? So you say, well, in a given time, I have a change in this direction time, okay, plus the change in that direction. So it's maybe an increase in volume or increase in temperature. Maybe this one is a decrease in that small volume. And in this case, in that direction, I have also an increase or decrease. But altogether, I add them up to get my resulting scalar. So the result of the divergence is a scalar, but it's applied to a tensor. So they are very similar and yet not. And finally, we have the curl of a vector, and this one is applied also to a vector field or a tensor, but the result is also a tensor. Okay, and you will get, so you need to have the ijk, and you have the operators, and now you have the components of the vector. And you treat it as a field. And basically, the Laplace operator, which we will use a lot. And that one is basically the divergence of the gradient. Okay, so if you apply the gradient to a field, you will get a vector and which returns a field. So this is the expression of the Laplace operator, which is nabla squared. So you will see those appear very often whenever we do any kind of operations in fluids or heat diffusion, et cetera, et cetera. It comes, that formula, those operators come back very, very frequently. In terms of stress, if you consider a body subjected to stress, a force is, an object is subjected to the action of a system of external forces, right? So you will have stresses in the different direction, and you need to express the stresses acting on that object. Now, unlike pressure, pressure is omnidirectional, so it's a scalar field to begin with, right? But stress itself is directional, okay? And you will have different components of stress. You have normal stress, you have shear stress. So you need to define the state of stress of an object. So let's say that you have an object and you remove part of it. Okay, so we imagine that we want a free body diagram. And so now we have a normal force perpendicular to the plane through which we have cut it. And we have an increment of area, delta A represents the difference in area. So we need to know which is the plane. We need to know the plane on which we want to measure the stress. We need to know the direction of the stress and the magnitude of the stress. So the stress vector, therefore, will have a normal and shear components. Now, at any given point, there is how many planes that we can put in a given point? How many planes can I have at a given point? How many different planes can I have? Infinity, which makes it a little bit complicated to express the state of stress at a point. So when I say what is the stress at point P, it's not a clear question. When I ask you the pressure at point P, you can give me a single value. When I ask you for the stress at point P, there's not a single answer, right? What stress do you want? So you need to define the coordinates of point P. You need the orientation of the plane through which it passes. And then you want to know if it's the normal or the shear stress. Only then can we say what is the state of stress, okay? Normally, in finite element and non-numerical methods, normal and shear stresses are positive if they point in the direction of the coordinate axis. Okay, so we assign the coordinate axis, and that's the direction of positive stress. So how do we define the state of stress at point P? We cut the object in two parts. We remove a part, but we keep all the internal forces as external forces to maintain equilibrium. And we consider the increment of plane A. And we divide the resulting force by the area to find the stresses. So the normal force over the area is the normal stress, obviously. And as the area tends towards zero, the ratio of the force toward over the area tends towards the shear stress. And there can be two shear stresses in two different directions acting on the same point on the same plane. Now, whenever you're going to look into the literature, you will see that they have different values or different notations. Different notations for the stresses in different directions, okay? So we need to identify whether the stress is a normal stress or shear stress, and we need to identify the plane on which it acts. So typically we will have, we can have X1 or X, Y, Z is a formal notation, or we can call it X1, X2, and X3. Why would we call them all X? Maybe this will give you an idea why we call them Y. See, if I call them X, I need two indices for my stress, and my stress, I just call it sigma. So the normal stress in this plane, in plane X1, becomes sigma 1, 1. Because it's normal, it's on plane 1, so it's on plane 1. So it's normal to 1. And because the second index is the same as the first one, it means that it's the normal stress. This is the shear stress. I know that it's shear stress because the two indices are in two different directions. It's still on the plane of the x-axis or x1, and it's going towards the direction of axis x2. And this one goes toward the shear stress going toward the direction of x3. So you may wonder why write it like that instead of x, y, z. Well, simply because look at this. When you have a matrix in memory and you have to address the cells in that matrix, notice this is index 1, 2, 3, 1, 1, 1, 2, and 3. So you have the row and column index basically built in. So it makes it easier to express, to convert your equations maybe that you have written with these indices into code that you're programming. Okay? When you do the transition from writing equations to actually implementing it, it's easier to keep your notation like this. And this is why you will often see the notation in this way. Of course, not everybody will write it like that in the papers that you will review. Okay? And so often you will have it seen as sigma xx, which is normal stress in the x direction on the x plane. Shear stress, the xy, that's xz are shear stresses pointing in the z direction, pointing in the y direction, etc., etc. So that's a bit more of a visual way of representing it, and you will also see it like that. It's less practical for implementation point, but still, it's not a big stretch to go from that notation to understand that X is plane 1 is row 1 and column 1, Y is row column 2, and so on. And finally, another way that is also used to represent them is by using not only sigma but tau for the stress. And in this case, tau is automatically the shear stress. Because sigma is only normal stress in this representation, you don't need to have two indices. So usually you'll have only sigma x, sigma y, sigma z. And tau will have two indices because you need to identify both the plane in which it acts and the direction which it acts on that plane. Okay? And this one is probably the one you are more, you have seen more often. But when you go through papers for the little term paper, it may not necessarily be the most common you will find. Okay? Sometimes the other two are more convenient because if someone has been writing code, it's often easier to express that code with the other notation than with this notation, just because you're thinking in terms of your rows and your columns, right? And it just makes it depends what code you've done and at what level you've been implementing code. Yeah.
Is it easier to just use number notation if you have multiple?
Yeah, well,
Okay.
it's an individual, ultimately, it's an individual preference. But if you are doing a lot of coding, it does become easier to just see rows and columns like that. Some people may get confused because confuses them with the nodes and the indices, so they might prefer to go with some. It's individual preference ultimately, okay? What I mean is that you will encounter the three types of notations when they're discussing the individual elements of a stress tensor. So be prepared to see that they exist and that they all mean the same thing. Okay? It's not because it's written in those three different ways that they mean something different. The three notations mean exactly the same thing. And once you have accepted that, you can proceed. So any of those three notations is a valid notation, okay? Just remember that. So one thing to remember is that the matrices are symmetrical. By that, I mean that the state of stress will always be symmetrical. So sigma x, y, and z will have their values, but then tau yx will always be equal to tau xy, or sigma 1, 2 and sigma 2, 1 will always have the same magnitude. Okay? The same thing with sigma 1, 3, 3, 1, sigma 3, 2, 2, 3. They will always be the same. So do you need to represent them with all these terms? No, and very often it is solved by representing the stress tensor as a vector. This is very commonly used whenever you're working with finite element programs. Okay, so at the stresses at each node have you solve for 6 values. Okay? And it's very useful because you've essentially removed 1/3 of all the values. And when you think of your matrices that are square, 1/3 means that you are 1/9. So your matrix, if you were to represent all the values of the individual elements, individual nodes, knowing that 2 of these nodes would be repeated. Okay? So if you remove 1/3 in a square matrix, you have removed basically so it would be 3 times as big, so 9 times bigger. Okay, so it would be much bigger because you had to square everything. Okay. So always keep that in mind, that it's important to remove any element that you can in your matrix. Okay, we'll leave it there for now. I see what I have next week. So next week we will be talking about the stress projections and so on. I like the first week. Once we get into the finite difference method and its applications, we will take a bit longer because I like to make solve problems in class. Okay, so today will also be a little bit shorter than usual. But once we get to the more numerical, sometimes they get a bit longer, so don't despair. I'll make sure to waste some of your time at some point. But for now, are there questions about the project and how to select topic? Any questions about, yes?
Are there any limitation? What's the limit for the group?
That's a good question. There is no. I would say try to do it before November 1st to select your group so that you can start discussing. I think you will probably not finish your project before doing the presentation. So your presentation will be done when you're maybe, because the project can be submitted at the same date as the final exam. Okay, whenever it's set up in the system. So that will be the deadline to submit the written report. However, the presentation will be done at on the last lecture. It will be an online presentation, so that we can accommodate everyone, those who are here, those who could not come because of visa reasons or other, which has happened every year since COVID. So because of that, it just makes it a bit easier to run the presentations. Okay, so November 1st, I think, is a good date for making sure that you have identified who else is in your group. So do it as fast as possible, basically. Okay, I would say the earliest that you can, but definitely it has to be before November 1st, at which point you will be working on preparing a presentation for sure. Okay, because the deadline is coming up at that point. But you should definitely be thinking about your topic and what you want to start reading about in the meantime. Okay. I will be posting samples of past exams also, so you have an idea of how scary.
There's gonna be like a midterm or something.
No midterm.
I think there is no final exam. I thought there is no final exam.
Last year, there was not the overwhelming majority of the class begged me to not have an exam.
I beg you to.
So if it's common, last week I was getting the feedback from your looks that you wanted an exam.
No, not at all.
Oh, okay, I misunderstood then. Okay, then it will probably be in the system with an exam, but if people prefer not to have an exam and put everything on the term paper, I have no problem with it. It just gives me one thing to correct. But I will still post some past exams so you can look at and see what's important to remember from it. Okay? Yes.
When do you think we should get started on the project?
My advice is as soon as possible, just because you have other classes and other projects and other things. And this is mostly reading and putting together ideas. It should not be hard. Okay? It should not be too hard to put something together, just get some reading done, right? And I don't know what you have in terms of projects in other classes, and how much work you will have to put into it. So my advice is always, if you can, get it done as soon as possible, so that the things that need more work, you have more time at the end.
So just to get it straight, we have to do a literature review, and then based off of that, we have to build a numerical model.
If you feel like building a numerical model, what I'm asking for you is that your explanation should be clear enough that I could implement what you are talking about. You don't necessarily need, there's often someone who likes to code or build something and they like to provide something. If sometimes some of those topics are, how do you use, say, finite element to calculate a factor of safety? So you can describe it, but one of the things that people on that topic in particular, people find easier for themselves to understand and then to explain is to actually use, in that case, you would not implement the finite element model, say, you would use a package that exists and you would run, say, a slope stability software, and then you would use finite element software on the same problem, the same geometry. So in that case, you do not necessarily implement the numerical method itself, but you implement the technique in a case study. That's something that people often find helps them explain themselves, because sometimes doing it is the best way to explain it in a way that someone else understands, you know? So that's one thing that that often happens. You don't have to, okay? It's something that many people like to do, but the ultimate goal is for you, when you present a technique or a numerical method or a technique using a numerical method, just by you reading your paper, I should have the feeling that by just reading your paper, I can sit down at my computer and implement either the technique using package software or the numerical method myself. Okay? Your explanation should be clear enough that I could follow it to implement it. In that case, you have met the goal, okay? So I'm not looking for a thick, because if it's too thick, you know what? I'm gonna read it and I'm not going to be able to implement it because I'm gonna fall asleep halfway through, okay? So there's a fine line between having enough explanation and having too much explanation, okay?
Just like we have to,
I mean, you still have to have the structure of a text, an introduction, and at the end, a conclusion. So I expect to have a formal paper, but I don't expect it to be a book, okay? As few pages as you can manage with having a nice structure to explain sufficiently clearly what it is. And again, don't go overboard in adding, okay? It does not help to make things wordy. It's actually very often it makes it more difficult to understand what you mean when if it's too long, if it's too wordy, if it's too, okay? Equations will be necessary, of course, but don't go overboard with equations, okay? Try to use the equations that are needed. But if it, again, if it's too many, like my eyes glaze over and right? So you want what is needed to make it clear. Maybe if you want to see, oh, this is how I build, because if you talk finite element, you go from the element matrix, and now you have the stiffness matrix, and you have to build the global stiffness matrix. And then you have to say, well, I have to go to that element, and so explain how you build it as simply as you can. You know, this element goes here, and then it goes there, blah, 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 you mark it. So, I mean, it's still a challenge to express yourself clearly for little things like that, okay? You have to appreciate that. But if you can manage it, again, the goal is to optimize the word count, okay? Don't go for big. Smaller is better. Okay? It has to be sufficient, has to have sufficient information to make it clear and no more, okay? That's the real goal. That's the essence, that's the secret of technical writing, okay? So you're not writing a novel this time. I know, we all wanted to have a little novel in the works. So that's not the purpose. Okay? So I don't want to have 50 pages.
okay, I know that. Or some price with like some.
I will go,
About the product.
yes.
For anyone interested,
For what?
the thermal hydro,
Good.